Welcome back to ECE 441A. Today is the due date for lab number 2, homework number 6, and I think we'll have homework number 7 due before exam number 3, but I just want to get you thinking. We do have another exam coming, and that's the Friday before the Thanksgiving break, and that's going to be upon us rather quickly. But it will be dealing with root locus design and construction. We're actually working on the construction of root loci now, and hopefully we will start to learn how to design. And essentially, the design process is we're going to have 2 shakers. Everybody's familiar with a salt shaker and a pepper shaker. We're going to have a pole shaker and a zero shaker, and we want to sprinkle poles and zeros onto our S-plane to shape the root locus. So we're trying to now design controllers by the selective placement of poles and zeros of our controller's transfer function. That's where we're headed, but before we get there, I want to review the 2 conditions behind the root locus rules, and those are the magnitude condition and the phase condition, and I'll quickly slide through that. And then we will start discussing these various rules. And these rules are not hard and fast in that they always have to be applied or used. In some circumstances, you may not use them. If you're driving a car, there's a lot of rules that you learn or strategies that you learn, but you may not use them on a particular or a given trip. You may not have to parallel park, but maybe you need to know how to parallel park. Maybe you don't need to back in park, but you might like to know how to do that. Well, these rules you can think somewhat in that same way. Sometimes you apply them, sometimes you don't, but in sketching these root loci, you might want to just have this list of rules on the side, and you can refer back to those as a guide as to what you want to do when. But traditionally, the first 2 are going to happen. Those you will do, and then what you do beyond that depends on the collection of poles and zeros that you have in your problem. As a review, here is our conventional or generic block diagram. We have a controller and we have a plant, and that combination, a lot of times we may just collect into one transfer function in the upper plant, which we will call G of S. What we are adjusting is this K, and that's the knob that we will be manipulating from 0 up to infinity. And in this class, we will actually be focusing on the negative feedback situation, which then results in, when we perform the closed loop transfer function, that gives us our 1 plus K G of S H of S in the denominator transfer function. And the 1 plus K G of S H of S is what influences the characteristic behavior of our system, and that's really why we want to change maybe the closed loop poles, is we may not be happy with where the dominant poles are living in the complex S-plane. We know where those complex poles might need to be based on our performance specs. We have settling time specs, and I do settling time, and I'm now thinking of a vertical line that I'm pushing possibly further into the left half plane to speed up the response. We might have peak time specifications, which is now this horizontal omega sub d line, and if we want a quicker response, we may want that imaginary part to be longer or further away from the real line. We also have percent overshoot specification, which is the angle, and that is influenced by the damping ratio or the zeta. But this we've already looked at in the past, but you should have this really embedded in memory at this point in the semester, this generic block diagram configuration. And what we want to play with now is understanding when we adjust K from 0 up to infinity, how do the closed loop poles, or the roots of this characteristic equation, how do they move around in the S-plane? I said we will focus on negative feedback in this class, and that's going to then give rise to this characteristic equation in the denominator, 1 plus k g of s h of s, and we can now solve that for k g of s h of s. Remember, g of s may have buried inside it poles and zeros of our controller, and we may be able to insert poles and zeros in g of s in order to influence our behavior beyond just adjusting the gain k. But with this characteristic equation written in the form of k g of s h of s equaling minus 1, and then viewing minus 1 as a complex number, having a magnitude of 1 and an angle of minus 180 degrees, that's actually what gives rise to all of the root locus rules, or those two conditions. We have a magnitude condition. The magnitude of k g of s h of s needs to be 1, and that will then determine where our roots are, and k g of s h of s has to have a phase of minus 180 degrees. And those will all then give rise to our rules for sketching the root locus. And here I've simply diagrammed out the point minus 1 in the complex S-plane. Obviously, you move 1 unit away from the origin to get to minus 1, and you go either minus 180 degrees or plus 180 degrees. And since typically we have lag or time delay in our system that corresponds to a negative phase, I like to simply usually use this minus 180 degrees or multiples of that when I refer to minus 1. So minus 1 will be 1 at an angle of minus 180 degrees. So what's the role of h of s? H of s is actually, could be a piece of your controller, but it may be sensor dynamics. It may just be additional dynamics that are filtering your output signal y of s. And h of s may be fixed, or you may have the liberty to adjust that. A lot of times h of s in our class will be 1. We'll just have unity output feedback, and it'll be negative. But h of s is written in this 1 plus k g of s h of s to remind us that it's potentially there. A lot of times we will just have nothing, or just a straight connection of 1 as h of s in the feedback path. What I've indicated here in red then is really what you need to be thinking about when you're sketching a root locus. The points on the root locus is going to be this pattern in the complex S-plane, and that pattern actually is where your closed loop poles can potentially live for that collection of poles and zeros in your system. And those roots, those closed loop poles, obviously are governed by 1 plus k g of s h of s equaling 0. But if you solve that for k g of s h of s, that says that all points on the root locus have to have an angle of minus 180 degrees, and the k to get them to that point is such that k g of s h of s has a magnitude of 1. Those are our two conditions. We have the magnitude condition and the phase angle condition, and we'll use these now as we progress through our rules of constructing the root locus. And typically we write this 1 plus k g of s h of s as having a numerator polynomial and a denominator polynomial, and we refer to little n of s and little d of s as our open loop, and that's in quotes. They may not actually be the open loop. It may depend on how the system is configured, but we will just call them or refer to those as the open loop poles and zeros. That's our standard root locus form. And what we want to do now is use that to create these root locus construction rules. And in the previous lectures, if we had a characteristic equation that was very generic or arbitrary, we know now how to convert it into this standard form by dividing out all of the terms that do not contain the parameter k. Let's now get into the root locus construction rules. Oh, and before I get too far, I should point out that somebody in office hours was showing me their notes, and I had made a typographical error last time. This should be the real axis segments on the root loci. I think I had, in my haste to write this before, and I've already corrected it in the previous day, but this is real axis segments on the root locus, and we'll get to that in step 2, but that's our French bread. That's the one that involves the French bread, if you've been paying attention to the lectures. So stay tuned. There's always a food theme somewhere, usually. Starting and stopping or starting and ending points of the root locus. Rule number 1. The root loci branches start, that's with k equal to 0, on the open loop poles. And remember what we are saying we're defining to be the open loop poles. Those are the roots of that little d of s polynomial in the denominator expression. So we're starting our root loci branches on the open loop poles, the roots of d of s, and some of the branches end that's as k gets big or k goes to infinity. Some of the branches end on the open loop zeros. And the open loop zeros, we are saying, are the roots of that numerator polynomial n of s in our standard form. Anticipating that some of you are going to ask, what does sum mean? We always need to worry about these vague terms. Sum really corresponds to the number of finite zeros. Those are really the roots of little n of s. Depending on the degrees of our n of s and d of s polynomials, we might have zeros at infinity. If d of s is fifth order and n of s is second order, there's a pole zero difference of 3. We have actually 3 zeros at infinity. And the branches associated with those zeros at infinity are the ones that are defined by the asymptotes, and those are going off to infinity. They aren't going to be fixed on this visible piece of our finite S-plane sketch. So the other branches approach the zeros at infinity. The rationale behind this rule, and this rule is so easy, you're going to say, why did you use so many words and so make it so difficult? It's not difficult at all, okay? But this is our characteristic equation with n of s and d of s identified. If we put that over, we want that to equal 0, and the best way to see that is to obtain a common denominator for both terms, which now says that really we're interested in this equation governing our behavior of the closed loop poles, d of s plus k n of s. And in this case, you can see that when k is 0, What values of S satisfy that equation? Well, they're exactly the same values of S that satisfy D of S equals 0. And those are the roots of D of S, or those are the poles, open loop poles of our standard form. Then as K gets big, Kn is going to dominate D, and so the roots of N of S are going to be the roots that satisfy that expression. That's this transition from K equals 0 up to K big, and why we have starting points at the open loop poles and ending points at the open loop zeros. Let's look at an example so that you now see how trivial this particular rule actually is. Suppose that somebody says we have a G of S containing a finite zero factor of S plus 1 and two pole factors, S plus 2 and S plus 3. And suppose they also say that we have an H of S. There's the H of S that was being asked about. Let's say that that's S plus 7 for the zero factor and S plus 5 for the pole factor in H of S. And in our sketch, in our diagram, we will define our open loop zeros, which I think we've already been sketching, but let's just be clear. We're defining those as these circles, and the open loop poles are the X's. So now we have X's and O's. If you're comfortable with football or basketball, this is now our engineering X's and O's. Okay? We like to have fun too. So now our playing surface is the S-plane. And we're going to be populating that S-plane with X's and O's. And then the patterns that these X's and O's will generate is the root locus in this case. But first, all we have to do is identify where to put them on the complex S-plane. Here's our S-plane. And let's say here's mine. If I'm interested in the open loop poles, where do I put my X's for this combination or this example of G of S and H of S? Minus 2, minus 3, and minus 5. Those are the poles of G of S, H of S. This is pretty easy. So whatever you just said, minus 2, whoops, let me do this in blue. Minus 3 and minus 5. Those are the open loop poles, and those obtain X's. That might get you a half a point out of 100 on the next exam. But at least it's a start, right? Let's get that other half of point. To get one full point out of 100, let's label the zeros. Again, this is very challenging. It's now at minus 1 and minus 7. And that's rule 1. That's all there is to rule 1. But now we know that we're starting, when K is equal to 0, we're starting at minus 2, minus 3, and minus 5. And as we adjust the gain K, some of our branches are going to approach minus 1 and minus 7. And how many branches of the root locus do we have? How many open loop poles do we have? How many X's do we have? 3. So we have 3 branches. And sometimes segments, it looks like one segment, that actually constitutes 2 branches. One might be coming from the right and one might be coming from the left, but that actually consists of 2 branches. And that's sometimes a point of confusion. But we have 3 branches for this particular problem, which says then 2 of those branches are going to terminate on those finite zeros. How many branches do we have going off to infinity? 1. That's all we know at this point. So let's get a little bit further. Let's look at rule number 2, and this is the French bread rule. This is rule number 2. Have to try to make this interesting or fun. So rule 2 is concerned with the root loci segments, or maybe I should say, I could phrase this many different ways. So let me say now, root loci segments on the real axis, and sometimes I might say this as the real axis segments on the root locus. You see how confusing I can make it? But it's the same thing. So maybe I like the second one. The real axis segments on the root locus. Because right now we're wanting to divide up our real axis based on the poles and zeros that have populated our real axis line. And so if you view the real axis like a piece of French bread, or I should say a full loaf of French bread, now we are cutting that at each of these poles and zeros. Which means how many segments on the real axis do we have for this example? How many pieces of French bread do we have after we've subdivided it or identified the segments, the real axis segments, based on these poles and zeros? Everybody see 6? Okay, we're in a good point. Now, what we need to do is figure out which of those 6 segments belong to the root locus. That's the point of this rule. And here's how I will phrase that. A line segment, a real axis line segment, or a line segment on the real axis, is a part of the root locus if and only if an odd number, and that's a mathematical odd, that's not odd in the sense of strange. Odd is 3, 1, 5, just so that we're clear. Since this is Halloween, I want to make sure we're not wearing masks or being confused. Sorry. Everybody's confused now since I mentioned that. If and only if an odd number of poles, and this confuses people. I don't know if I should say and. I say and or zeros because sometimes we don't have zeros, so I'm just going to say and or zeros lie to the right of the line segment. And this odd number lying to the right, that really only pertains to the scenario where we have negative feedback. If we had positive feedback, then that would be an even. But I don't want to go there. Let's just learn the rules for negative feedback so that we're not confused. But if somebody starts telling you, oh, your root locus is here, and it looks opposite to what you're used to seeing, then you might start looking at what is the sign of your feedback. This is for negative feedback, and now let's go up and see if we can apply this to our previous example. If I look at the line segment from -1 to positive infinity, are there an odd number of poles and zeros to the right of that line segment? No, there aren't any poles and zeros to the right of any point on that. So if I looked at the origin, I have no poles and zeros to the right. So that segment does not belong on the root locus. What if I look at a point here? Is that point, does any point there between -1 and -2, does it have an odd number of poles or zeros to its right? Poles and or zeros to the right, and I just need it to be odd. Yes. So this segment between -1 and -2 does belong to the root locus. And why is that? We said all points on the root locus have to have a phase of -180 degrees. What's the phase of that 0 at -1 to any point between -1 and -2? Well, if I look at the angle between this positive real segment and that 0, I have to turn around to see any point between -1 and -2. The angle of that 0 is -180 degrees. Maybe I should have drawn it in the other direction so that you see it explicitly as I'm saying, and I have to be a little less aggressive with my eraser. Now, putting this back in is going to be a trick. All right, all because do we see that that contributes -180 degrees? Do I have your attention now? What's the angle from -2 to -1.5? What's the angle contributed by that pole at -2 to any point on that line segment? How far do I have to move my head if I'm looking to my right? If I'm -2 and I'm looking right, what's my angle? 0. I don't have to move, do I, to get... What about the angle from -3 to any point there that I've sketched as red? 0. Any of those poles and zeros to the left of that segment are contributing 0 degrees. So the sum of all of those angles is 0, except for that angle contributed by the 0 at -1, which is -180. All right. What about -2.5, or any point between -2 and -3? Is there an odd number of poles and zeros to the right? No. -3 to -5, an odd number of poles and zeros. -5, -7. -7 to -infinity. Those are the segments. The real axis segments, boy, that's a pretty bad straight line, isn't it? Looks much better if I just zoom in here locally, but if I stand back and look from your perspective in the back of the classroom, you can do a better job of sketching. Let me give you that before we get any further. Is there any question on which segments of the real axis belong to the root locus? Do you see why it has to be an odd number? We need the angle to be -180. If we looked at -2.5, then the 0 contributes 180, the pole contributes 180, that's a net 360. So that's not -180. That's where this odd comes into play. Let's look at another example. And the proof of this rule is really based on what we were just doing. Look at the phase angle condition. And again, that's all based on negative feedback, being a -180. Let's look at another example. Suppose I now have the following pole 0 pattern in the S-plane. Maybe I have a pole at the origin, a pole at, or a 0 at -1. Maybe I have a pole at -3. I have a pole at -7. I have some poles here. Maybe I have some zeros here. Now what do I do? If I have this French bread and I'm cutting it, how many pieces of French bread have I created for this pattern of poles and zeros? And my French bread is only on the real axis. I could care less about what's happening off the real axis, because those angles contributed by complex conjugate poles and zeros cancel each other out on the real line. So we have 5 pieces of French bread, or 5 real axis segments. Do I have a root locus branch from the origin to plus infinity? From the origin to plus infinity, does that belong on the root locus? How about from the origin to minus 1? From minus 1 to minus 3. I have an even number of poles and zeros to the right. That's not going to be belonging to the root locus. What about between minus 3 and minus 7? How about from minus 7 to minus infinity? How many root locus branches do I have? How many open loop poles do I have? Now I do have to worry about things off the real axis. How many open loop poles do I have? How many X's are there? We're going back now. We're going back to maybe preschool days, huh? We have 5. Especially since I saw a freshman at high school here in Tucson scored a perfect score on the AP Calculus AB exam as a freshman in high school. I always joke to you guys about, oh, did you have that as an 8th grader or as a 6th grader, your algebra or calculus? And I guess I'm not joking anymore. We have 5 branches, right? So we're going to have 5 closed loop poles for this particular configuration of poles and zeros. How many branches do I have between minus 3 and minus 7? That's where it gets a little tricky. How many line segments do I have between minus 3 and minus 7? 1, but I have 2 branches. One branch is starting at minus 3. It's going left. I have another branch starting at minus 7, and it's going right. I have 2 branches that are starting at those complex conjugate poles, and I have 1 branch starting at the origin. We're going to have to figure out how all of this fits together, but so far we've learned how to identify the real axis segments that belong to the root locus. Now what we want to do is what happens as we crank up the gain k to large values. Question? Pardon? So the direction of the branches are determined by the rules. And what we're going to see is that this, as we increase the gain k, that branch is going to, the pole on that branch is going to move from the origin to minus 1. This one is going to move from minus 3 to the left. Minus 7 is going to move to the right. And then they are going to split. And let me just give you a hypothetical. You might have, well, what do we have? How many poles do we have? 5. How many zeros do we have? 3. So how many zeros at infinity do we have? We have 5 minus 3. We have 2 zeros at infinity. That means we have 2 asymptotes. This is actually rule number 3. We have 2 branches that are going to go off to infinity in this sketch. And we will learn where those go, but let's just say that it might be that these go here, these come together, and then they go off here, and that might be the root locus. That, I say that might be, and we'll learn from the rules if this is indeed what happens. But do you see that 3 of those branches terminated and 2 go off to infinity? The ones that I have sketched from the poles are moving off to infinity as k gets big. And in this case, if we actually cross the imaginary axis, we probably have a limit on how much we want to crank up the gain K before we go unstable. But let's look at rule number 3. Rule number 3 is the asymptotic behavior for large K. And now the asymptotic behavior is going to come into play when the number of poles, and that's what I'm calling P, is not the same as the number of zeros. I'm using P as my variable for the number of poles, and Z is my number or variable for the number of zeros. In my last example, I had P equal to 5, and Z, these are the finite zeros, I should say. 3 was my number of finite zeros. Those are the values of S that satisfy little n of S. Those are my open loop zeros. And what this allows us to do is determine where these branches eventually go. These are just asymptotes. These aren't the actual branches, but they're guidelines that the branches move towards. So as you crank up the gain K, you'll eventually be approaching those asymptotes, or be basically right on those asymptotes. What we want to do now is say that we are finding asymptotic lines that help in the selection or in the sketching of the root locus. And now let me give you 2 ways of sketching these root locus. These asymptotes. One is going to be the angles. So the angles might be at minus 180, or it might be plus and minus 90, or it might be plus 45, minus 45, plus 135, minus 135. Those might be our angles. And then we have to figure out where are those asymptotes located, where's their centroid on the real axis. Let me try to state those two properties, the angles and the centroid. The root locus is asymptotic to straight lines with angles given by phi sub A equaling 2L plus 1 times 180 degrees divided by P minus Z. P being the poles and Z being the finite zeros. And L goes from 0, 1, 2, up to P minus Z. I guess I can widen my paper. P minus Z minus 1. So 1 less than the pole 0 excess. I'm going to be calling P minus Z, probably routinely, the pole 0 excess. In the last example, what was our pole 0 excess? It was 5 minus 3. It was 2. So L would then vary from 0 to 2 minus 1, or 1. So we would have L equal to 0 and 1 in this formula. Those would be our angles of the asymptotes. These straight lines, these straight line asymptotes, actually intersect at a point we will call sigma sub A, called the centroid. On the real axis, and that centroid is given by the following formula. It's now sigma sub A is equal to the sum of our poles of our G of S, H of S transfer function. We sum up all of those poles, and the imaginary components are going to cancel because they come in conjugate pairs, but the real parts of those complex poles will be important, minus the sum of the zeros of G of S, H of S, all divided by the pole zero excess. Let's look at some examples of that. An example 1, let's say G of S, H of S was this S plus 1. Now I'm multiplying G and H together. And we have that already sketched. Let me just re-sketch it. Maybe I can do a better job this time. If I'm quick with my line, it's easier. I have poles at -2, -3, and -5, and I have finite zeros at -1 and -7. And now, where were my real axis line segments on the root locus? It was here, here, and here. Was it not? Now, what is P? How many poles do I have? 3. What's Z? That's 2, so P minus Z is 1. What's my angle of the asymptote? So that's 180 divided by P minus Z, which is 1, times 2L plus 1, but L goes up to 1 less than my pole zero excess, and that's just 0. So I now have 180 divided, or times 1. My angle of my asymptote is 180 degrees, which says, where's my asymptote living? If it's going in the direction of 180 degrees, where is my asymptote moving or lying? The real axis, and it's going off to minus infinity, isn't it? Does it matter where sigma sub A is? No, I don't even need to calculate it. I don't care where it's centered. I know that things big are happening at minus infinity. So in this case, our angle is 180 because of our pole zero excess of 1, and our sigma sub A is not even necessary. Which says, then, that as I crank up the gain K, now I'm going to start putting in some shapes here. As I crank up the gain K, maybe, how many branches do I have? How many root locus branches do I have? This is a good example for that, but it's maybe a little bit confusing. How many poles do I have? 3. So I have 3 branches. Forget how many root locus segments I have. I actually have 3 of those, but some of those are doubling up. If I crank up the gain K a little bit, this pole is going to move towards the 0, and maybe it's going to go to this triangle. And this guy might go here, and this guy might go here. There's my 3 closed-loop poles for a small gain K. As I crank up the gain K a little bit more, what's going to happen? Well, those 2 poles between -3 and -5 are going to meet, and they're going to break away from the real axis. They will break away, and now let me just say that they break away here. And this may not be a circle quite, oh boy. It's symmetric with respect to the positive and negative branches. But now if I crank up the gain a little bit more, I now might move this guy to that point, and this guy might go here, and one of the others goes there. Meaning I have one branch that's in yellow, I have another branch that's in blue, and my third branch is in green. There are my 3 branches of the root locus. If I crank up the gain K a little bit more, now I might go to a cloud. I'm running out of symbols. And now everybody likes the cloud. They like to play in the cloud, so let's put some clouds on our root locus. And this one now is right there. That was a cloud and not a clown. Okay, you could go now and Halloween as a cloud, maybe not a clown this year for whatever reason. Now, if I crank up the gain even more, what happens? These poles are going in this direction, but now these clouds are going to meet back on the real line. One's going to go here towards the finite zero at -7, and the other one is going to zip off to -infinity. Which now if I use a different symbol, maybe now I have a star there. A star is off the page, but I'll just say it's in that direction. And another star is almost right on top of that 0. Question?
Was it arbitrary or?
So the question I think is, why did yellow go up and why did blue go down? And that was arbitrary.
Okay.
It doesn't matter. You just know that they break away. One's going to go up, one's going to go down. And it doesn't matter if you keep track of which branch is which, because they're going to appear as complex conjugate pairs. So this guy, maybe the blue, since I'm still blue, he might come back to -7. The yellow, he's adventurous. He goes off to -infinity. So there's one branch that goes off following our asymptote, and in that case it is right on top of our asymptote, the branch. The other branch goes from wherever we re-entered, which might be -12, and zips back to -7. Let's do another example. That one was kind of boring because where was our asymptote? It was at 180. So let's look at another example. Let's call this example 2. And let's say that now we have an h that's 1, and let's say our g of s is s plus 1, s plus 4, s plus 6, s plus 10. And we can quickly perform and those are all uniformly spaced, maybe not sketched uniformly, but that's supposed to be, I hope, -10. Here's -2, it's 4 -6, -8. I can quickly sketch a pole at -4, an open loop pole, an open loop pole at -6, and an open loop pole at -10, and I have a 0 at -1. And which root locus, or which line segments belong to the root locus? From -1 to -4, that's a part of the root locus, right? -4 to -6, yes or no? No. -6 to -10, yes. How many branches do I have? I have 3. So I'm going to have 3 closed loop poles. What's my pole zero excess? Let me just quickly... Now I have a pole zero excess of 2. 3 minus 1. What's my phi sub A? It's 180 degrees divided by that pole zero excess times 2L plus 1, where L goes from 0 and 1. So those angles are going to be at 90 degrees and 270 degrees. Now my root locus is going to go zipping off to infinity in the positive imaginary direction, another one in the negative imaginary direction, and we have to figure out where those asymptotes centered. And we'll pick up at that point on Wednesday.
Have mercy on the last part.